Every single day, trillions of dollars flow through the global financial system based on the mathematical foundation of one single formula. It bridges the gap between unpredictable human chaos and the rigid, beautiful laws of physics. This is the story of the Black-Scholes-Merton equation, a mathematical masterpiece that promised to eliminate risk, made physics professors into billionaires, and ultimately triggered some of the most catastrophic market crashes in human history. To understand why this equation was so revolutionary, we must go back to a time when financial markets were pure gambling. For centuries, even the smartest minds on Earth were completely crushed by market movements. Take Sir Isaac Newton. In 1720, he invested in the South Sea Company, a massive speculative bubble. Newton initially doubled his money and sold his shares for a massive profit. But as he watched his friends get richer, intense FOMO took over. He re-entered the market with almost his entire life savings at the absolute peak. When the bubble burst, he lost a staggering $2 million in today's money. Humiliated and broke, Newton famously noted that while he could calculate the path of the planets, human psychology was entirely unpredictable. For the next 200 years, economists assumed that pricing financial contracts accurately was mathematically impossible. To solve the problem that defeated Newton, we first need to understand the financial instrument at the heart of this story: the options contract. An option is a contract that gives you the right, but not the obligation, to buy or sell an asset at a fixed price in the future. A call option allows you to buy a stock at a set price, called the strike price. If the stock skyrockets, your potential profit is technically infinite, while your loss is limited to the small premium you paid for the contract. But how do you price such a contract fairly? If it is too cheap, the seller loses. If it is too expensive, no one buys it. The first massive breakthrough in solving this option pricing riddle came in the year 1900 from a French graduate student named Louis Bachelier. He realized that short-term stock prices behave exactly like a random walk. At any given millisecond, a price is just as likely to tick upwards as it is to tick downwards, driven by pure random order flow. Bachelier made a stunning connection. If prices bounce around randomly, their long-term distribution can be modeled using a Galton board. Each peg represents a random event forcing a price left or right, while a single ball's trajectory is completely unpredictable. Thousands of balls will always stack into a perfect bell curve. This meant that while tomorrow's stock price is a complete mystery, the mathematical probability of where that price could end up in 1 month is highly structured and beautifully predictable. Five years after Louis Bachelier published his radical ideas about the financial markets, the world of physics experienced an atomic revolution. In 1905, Albert Einstein published a groundbreaking paper that mathematically proved the existence of atoms. Einstein solved a long-standing mystery known as Brownian motion. Biologists had noticed that microscopic pollen grains suspended in water moved in a continuous, violent, and completely erratic zigzag pattern. Einstein proved that this was not alive. The pollen grain was being relentlessly bombarded by millions of invisible, moving water molecules. But the most staggering realization came when mathematicians looked at Einstein's equations. The physics formula used to map the chaotic collisions of atoms in liquid was mathematically identical to the formula Bachelier used to map the chaotic price movements of stocks. Wall Street and quantum physics were staring at the exact same randomness. To solve the core mathematical puzzle of the options market, financial theorists did not look at traditional economics. Instead, they looked directly into the beautiful laws of classical physics. In the year 1822, the brilliant French mathematician Joseph Fourier published a masterpiece on the analytical theory of heat. Fourier developed a partial differential equation to describe exactly how thermal energy diffuses through a solid object over time. If you apply intense heat to one single point on a metal bar, that heat does not stay concentrated. It flows outward, spreading into areas of lower temperature until the entire system reaches a smooth, calm equilibrium. 150 years later, Myron Scholes and Fisher Black looked at Fourier's physics equation and had an absolute epiphany. They realized that a stock price moving through time behaves exactly like a particle of heat moving through a metal bar. The uncertainty and potential price paths of tomorrow spread out and diffuse into the future in a mathematically identical way. In 1973, Fisher Black, Myron Scholes, and Robert Merton solved the puzzle. They created the definitive formula to price financial risk. However, the formula had a dangerous flaw. It assumed market movements always follow a neat, perfect bell curve, making extreme market crashes statistically impossible. But in October 1987, Black Monday hit, and the stock market crashed 22% in a single day. After that disaster, traders realized that extreme crashes happen much more often than physics models predict. To adjust for this hidden risk, options pricing changed forever, creating a permanent pattern known as the volatility smile. The neat mathematics of perfect bell curves had met the brutal reality of human panic. Armed with the Nobel Prize-winning Black-Scholes formula, Myron Scholes and Robert Merton joined an elite hedge fund called Long-Term Capital Management in 1994. They believed that by using advanced physics equations, they could completely calculate and eliminate market risk. For the first few years, it looked like magic. The fund made billions of dollars, and Wall Street hailed them as financial gods. But in 1998, the impossible happened. Russia unexpectedly defaulted on its government debt, triggering a massive wave of panic. LTCM's mathematical models had calculated that such an event was so rare it wouldn't happen in a billion lifetimes, because they had leveraged their bets hundreds of times over. Their perfect system collapsed in just a matter of weeks, losing over $4 billion. The crash was so violent that it threatened to destroy the entire global banking system. The Federal Reserve had to step in and organize a massive multi-billion-dollar bailout. The genius formula that promised to rewrite human risk had instead created one of the most catastrophic financial disasters in modern history. To push our understanding further, let us look at how probability diffuses mathematically. In the Black-Scholes model, asset prices spread outwards through a process called geometric Brownian motion. This curve tracking potential outcomes behaves precisely like a fluid spreading across a surface. The area under the curve always equals 1, representing total absolute certainty that the price must exist somewhere. As the timeline extends, the peak collapses and the variance expands. This partial differential expansion forces options traders to completely recalculate their mathematical exposure every second. The mathematical width of this spreading bell curve determines the premium of the contract. Beyond the standard metrics, Institutional market makers must track the second derivative of the option price, known as gamma. Gamma measures the acceleration of your risk. It determines how fast your portfolio sensitivity will destabilize when prices jump unexpectedly. Notice how the gamma graph forms a sharp spike. It reaches its absolute maximum when the stock price is exactly equal to the strike price. When a stock hovers directly in this zone close to expiration, gamma explodes. This forces hedge funds to aggressively rebalance their positions, creating massive artificial feedback loops that can trigger wild market swings. However, this beautiful physics model harbored a deeply dangerous flaw. It assumed that financial market movements always follow a neat, perfect bell curve where extreme movements are statistically impossible. But human beings are not water molecules. In October 1987, Black Monday hit the global markets, and the Dow Jones crashed 22% in a single day. An event that the models predicted should never happen in the history of the universe. After that absolute disaster, options traders realized that extreme human panic and massive crashes happen far more frequently than pure physics models predict. To permanently adjust for this hidden risk, the pricing of options changed forever, creating an iconic, curved mathematical pattern known as the volatility smile. The elegant mathematics of perfect physics had met the brutal reality of human fear. Fast forward to the modern era, and the ghost of Isaac Newton's FOMO is back. Just as investors in 1720 blindly bought into the South Sea Company, and LTCM believed math could outsmart human panic, today's markets have poured trillions of dollars into artificial intelligence. The valuation curves of tech giants look terrifyingly identical to the historic speculative bubbles of the past. If we compare the LTCM collapse of 1998 to today's AI trajectory, the structural parallels follow a terrifyingly steep curve, driven by massive speculation. The market shoots straight upward, building a monumental bubble based on uninterrupted mathematical growth. But once the trajectory reaches its absolute peak, reality hits the model. Whether it is an unexpected debt default or the realization that AI revenues cannot pay for the trillion-dollar hardware, the panic triggers an instantaneous shift. The steep curve reverses into an unstoppable vertical crash. Whether it is an options formula or a neural network, the ultimate breakdown occurs when we mistake a clean mathematical model for reality. As Newton learned centuries ago, you can calculate the motions of heavenly bodies, but you can never calculate the madness of crowds. In the end, the collapse of LTCM proved a vital lesson. The Black-Scholes formula is one of the most brilliant mathematical achievements in history. But when infinite leverage meets unpredictable human panic, no equation can save us. Markets are not just physics. They are a reflection of human psychology. And fear will always defy pure logic.